Hey everybody, this is the first lecture in Lambda School's computer science curriculum. The computer science curriculum is going to introduce you to what are my opinions to be the most fundamental aspects of computer theory and computer hardware that you need to know in order to be a better programmer. Not every element of computer theory is essential to being a better programmer, in part because you can specialize in any subfield of computer science deeply enough that you don't end up programming at all. You just study that one special subfield. So throughout the entire computer science curriculum, I will be hyperfixating on very small details of the overall system and completely ignoring other deep fundamentals that, in my opinion, you don't need to know as much of in order to speak well about software and about writing web pages and mobile applications and user interface applications, databases or data structures. A lot of this stuff, a lot of the real basics of computer science, you won't need to know, but some of them you will. So that's the purpose of this first lecture. I debated at great length about the best way to explain your computer to you. And at first, I thought that I would show you the picture of the inside of your desktop and tell you what all the parts are. But I realized that I'd forgotten something more fundamental than that, and that's logic. We'll come back around to logic and we will learn it in more detail. But before we do that, I need to tell you the story of how to build a computer from scratch. So that starts with, I'm going to start a screen share, the invention of the transistor, which hopefully most of you have heard of. And truth be told, I'm not an electrical engineer, and I don't have a full understanding of the electrical behaviors of transistors, how to build them, and what makes them so special. My basic understanding of how a transistor works is that it enables an electrical designer, an electrical engineer, to control the current on an output wire or a pair of output wires based on the current of an input wire. And there's many different ways of building a transistor, I think. Anyway, before I say more things that I don't understand, I'll just point you to this transistor page. It's full of electrical engineering theory that I have limited understanding of, including this simple diagram. It's got an in and some other current and a ground, and something causes the signal to change. Okay, so using a transistor, electrical engineers realized that they could build, and this is way back in the day, I want to say 1935, but I could be wrong. Transistor engineers realized that they could build logic gates. And a logic gate made from transistors is the real fundamental aspect of a computer. Everything inside of your computer is either a capacitor, which is essentially a tiny battery, or a wire, or a clock signal generator, which we build from tiny, tiny little circuits that oscillate and generate a signal, and from transistors. And the CPU inside of your system has many billions of transistors in it that we will get to in more detail. And each of those transistors is a subcomponent of a logic gate. Okay, so let's see. Logic gate, 1886, it was proposed that such a thing could be done. 1807, one actually created one, it looks like. So anyway, this is a very old technology, but it couldn't be built for a long time. And then in the 40s and the 50s and the 60s, it could be built, but it wasn't very small, right? And that's where semiconductors became valuable. It was semiconductor transistors that became shrinkable, okay? At first, computers were built with vacuum tubes, and vacuum tubes could function like a transistor, but they were large, and they were hard to reproduce, and they were expensive, and so all the computers were as big as buildings. I'm off the cuff here theorizing about it. You know, the first semiconductors used for building transistors were built in the 50s or the 60s maybe, and it turns out they're very easy to automate. A semiconductor, and again, I'm not an electrical engineer, but the mechanism of a semiconductor is that they are able to, using sophisticated machinery, this is like a printed circuit board. That's kind of the biggest, dumbest version of a semiconductor. And actually, it isn't a semiconductor, but they're related. Okay, a semiconductor has a base layer that's very thin, and then it has another layer written on top of it that is also very thin, but it has grooves in it, okay? And those grooves are taking advantage of the properties of semiconductor electrical behavior. So they put another layer on top of the semiconductor, and when they give it a specific current, when they maybe warm it to a certain temperature, they give it a specific current, it makes it so that those depressions in the semiconductor surface become conductive. The thick part of the semiconductor doesn't become conductive, and the depressions do. And that small shapes in those very, very flat layers of semiconductor material become transistors. That's what a semiconductor is. Okay, so they started out building semiconductors that were large, that you could trace by hand with a pen or a pencil. And then iteratively over the last 60, 70 years, we have developed technologies for printing semiconductor chips on silicon. Silicon dioxide is the premier semiconductor. It's the one that's affordable. You can make it from sand. And using more and more and more refined engineering techniques, unbelievably advanced engineering techniques, we've scrunched down the size of a transistor to be nanometers, as small as it possibly can be almost, on a tiny, tiny piece of silicon. And then the same principle is applied. A current is applied to it, and it magically becomes a wire tracing pattern in a very, very small space. Okay, so inside of that CPU that's being built, and any other chip that you use, everything that's happening there is being made from combinations of logic gates. Okay, and logic gates are made from transistors. Unfortunately, I can't give the best background on how to build them. Like, how many transistors do we need to build a NOT gate? Or how many wires in does it need? With a little bit more research, I could show it to you, but I'm not ready for that today. So the way that a NOT gate works is through a single wire in, the current gets flipped. Okay, now this gate has a hidden wire coming into it that's providing power, most likely. Okay, so if a NOT gate has no current in it, it produces a current on the outside based on the way the transistors have been assigned in this very small electromechanical space. And it has a power wire coming into it that's not shown, so that if there is no current here, current will come out of it. And I could even be wrong about that. Maybe it doesn't have a power wire. Maybe the function of the semiconductor causes electricity to emanate from it when it doesn't have current being applied to it. Okay, this is the most basic gate. And then using other combinations of transistors, you can build AND gates such that if this wire has power and this wire has power, then the output wire has power. Okay, and each one of these logic gates comes with a logic state table that says, so imagine that wire 1 is A and wire 2 is B. Okay, if A is 0 and B is 0, the output is 0. If A is 0 and B is 1, the output is 0 because it's an AND gate. It only works when they are both, when it is A and B. All right, so we see A and B produces 1. Or an OR gate drawn this way. If it's neither, it produces 0. But if any of them have power, then the output has wire or has power. Okay, and using these basic gates now, you can add a NOT to an AND to build a NAND, which is a different state table. It produces power when there's no power, when there's OR power, but not when there's AND power. You can have an inverted OR gate, and you can have an exclusive OR gate, okay? An exclusive OR gate has power only when it's one or the other, but not both. And then this exclusive NOR gate is either neither or both, but not each by themselves. All right, so this is it. These are the basis. I don't see any more listed here in the logic gates, okay? Your CPU inside of your computer, whether it's like what, a Pentium or a Celeron, or whether it's an i7, is very carefully designed by hardware engineers, and they have tools that build hardware for them, but someone at Intel has essentially a map diagram of every logic gate inside of your CPU, and it has wires that go into it and wires that go out of it, and those are mapped along all these logic gates. All right, so I realized that I had to touch on logic gates, and we will have a more challenging exercise about logic gates in a few weeks. But I had to make sure you knew what you were looking at. This is the core of all digital computing. It's only logic gates, and those logic gates are used to compute arithmetic, and from that, computers are born. All right, so I'm going to pull my lecture slides down here. Lecture slides. This is the GitHub README for Computer Architecture 1. You can all access this README, and I want you to read through it after you watch this recording. And I want you to scan or skim the preparatory material, the other links that I put in here, because you'll want to know it all. All right, so I made a very simple drawing here that shows the basic connections inside of your computer. Some of you may know this already if you've been working IT or you build your own computers. For those of you who aren't coming into Lambda with an IT background, this material is essential to you. All right, so I wanted to put a bigger box around the CPU because the CPU truly is the central processing unit. It makes everything else possible. Now, every component in your computer has some kind of processor of its own. The difference between a CPU and a processor that's on any piece of hardware that you can see. I've got, well, my phone here, for example. Well, it's got a CPU, so it doesn't count. Here's maybe a better example. Okay, this is the TV remote for my monitor. It's got a CPU in it of some kind, but it's not generic. It won't do anything. It was designed by a hardware engineer to do one job. And so the wires that go into it are physically deterministic. When I press a button on this baby, it closes a wire that passes through a gate that causes a light to emit from this. It's physically deterministic. But the CPU inside of your computer, while it is also physically deterministic, it is infinitely configurable. And that's the wham bow that caused this stuff to begin. It's called a generic Turing machine, or there's a better word for it that we will cover in a near lesson for you. A Turing machine was invented by Alan Turing to be a general purpose computer. He proposed this mathematical theory that if we made a machine that could store a value in a specific place and do an operation on that value, and then store the result of that value in another place, and then read the next instruction that it was supposed to do from another place, you could compute anything that can be computed. And he proved it mathematically. He said, if you could make a system that could do this, you could compute anything that's possible to be computed. And that is what your CPU is. And if that sounds exciting or impressive, it is exciting and impressive because in the limit, in the infinite amount of computation that could ever be done in the extension of all time, your CPU can do it. Now, luckily for us mortals, it turns out some problems are so hard they can't be computed at all. They're too hard to compute in a linear sense, which we will also be learning about. Okay, the CPU is this general purpose machine that connects to the rest of your computer through buses. The CPU has, in your computer, 99% chance it has a 64-bit bus. And what that means is that there's 64 wires coming out of it that contain a single message, that contain a single word. And in the most general sense, every clock cycle, okay, your computer has a certain hertz, megahertz or gigahertz. 3.4 gigahertz is a pretty fast one. 2 gigahertz is a pretty average one today. What that means is inside of your CPU, there's a little clock element. Remember I told you there's transistors and there's clocks and there's capacitors inside of there. There's a little clock piece of hardware. When you apply power to it, it makes a sine wave. It goes up and down really, 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 really fast. And I've got this Wacom tablet that I was going to draw a sine wave for you because it's fun to draw stuff in a lecture like this. But they wanted me to reboot my computer after I installed the drivers. And so it's like, table flip, throw this over my shoulder, whatever. I'm not restarting my computer. Ask me next month because I have a Mac. Haha. Okay, sorry, I got myself derailed. Okay, so the clock goes like this, up and down 2 billion times per second. That's what 2 gigahertz means. 2 billion times per second, the clock goes up and down. And each time it goes up, it activates a circuit inside of the CPU that can change the data on that bus, that 64-wire bus. The CPU can say, I'm going to read the wires that are on that bus. There's 64 wires, and each one of them can be either on or off all the way through. All right, so this points to another aspect of computer science theory, and that's complexity or data encoding or bandwidth, okay? What I'm getting at is that this 64-bit bus, it's got 64 wires in it, and each of the wires can have a special value. And it turns out that that package can contain a huge number of possibilities. 2 to the 64th is how many possibilities that it can contain. Okay, so all the possible messages that can be passed over the 64-bit bus make for a pretty large space of complexity. But even better than that, the computer has memory, so it can store one of those 64-bit values and save it somewhere else, and then read another 64-bit value and save it, and then write and then multiply them together or add them together, and so on. All right. Throughout our computer science curriculum, I'm going to be switching between a mode where I talk about what I've understood to be the latest in the technological space, which is changing very quickly, or I'll be talking about a theoretical basic design, okay? And the theoretical basic design goes all the way back to Alan Turing. It goes all the way back to John von Neumann when these guys proved that you could build a computer like this, and they proved how powerful it would be. And they said, if we build an integrated circuit that has these properties, we can build a Turing machine with it. Okay, your computer was built using those theories so that it works as a Turing machine, but it has had all kinds of cool new stuff grafted onto the edges of it to make it more powerful. Okay, so the bus is my favorite example of this, okay, because your modern CPU, it has 2 primary buses, all right, and, oh, this is not updated. I think if I refresh it, it will be updated. No? Oh, that's strange. So GitHub has cached my file. This is called camo.githubusercontent.com, but that's not right. Because here in my file, this is the path. https://www.lucidchart.etc. So for some reason, GitHub has cached that file. Let's see. I've made a small change to this document, so I'm going to push it. maybe then GitHub will refresh the file. If it doesn't, then we will just load it directly. Because GitHub is caching this image. GitHub doesn't want to load it every time. So if I just paste it in here, fingers crossed, it worked, okay? This is what's supposed to appear in this document, and technology will block you at every turn. Okay, so the CPU has two primary buses to the outside world now. 15 years ago or 25 years ago, it had one bus, and it was somewhat easier to understand. The CPU, say 20 years ago when computers were 32-bit, were they? Oh yeah, 97. Computers were 32-bit. They had 32 wires going out to the rest of the world, not 64. And those 32 wires were shared among every machine that you plugged into the system. So you had a CPU sitting here, and there were 32 wires coming out of it, and they all shared, that's the bus. That's what a bus means. They all shared the wires. So if you put a hard drive on there, it would be connected to those 32 wires. If you put a graphics card on there, it would be connected to those 32 wires. If you put RAM on there, of course, it's connected to those 32 wires. Every other peripheral, more or less, connected to those 32 wires, and the CPU controlled them directly. It timed them. The CPU had the ability to say, hard drive, I'm about to tell you which wires to set, and then it would set those wires. The hard drive would get them, and it would perform an operation. Today, the computer has more, your CPU has more abstract buses between it and the rest of the hardware. In particular, it's got two buses, as you can see on the screen. There's an I/O bus, which connects the CPU with your primary peripherals. Okay, and the PCIX bus is not at all like the CPU's I/O bus. The PCIX bus is called a serial bus, meaning that it's got a whole bunch of wires that deliver data 1 byte at a time. And it can connect, I can't remember, I read it shortly ago. It's got something like 36 wires. And each pair of those wires can make up one stream of data, and it connects them to your network interface card. It connects them to like your TV capture card, and it actually, I believe, connects to your USB bus. So the CPU has a direct line to all those peripherals in one direction. The CPU also has a direct line to something called the DMA bus, or the direct memory access bus is what it means. And the DMA bus used to be kind of the main bus, kind of the only bus. And different peripherals had to control memory through the CPU. Only the CPU had the power to control the memory. And so in order to improve speeds, that's what all of these changes over time have been, is hardware engineers at Intel and AMD and other companies like Texas Instruments and Qualcomm now in particular, and CSR. These guys are all building CPUs. You don't see them as much, but they're doing it. Apple was building CPUs for a while. They have discovered, those engineers, that they can't make it run faster unless they change the architecture in a certain way. So the DMA bus is very important. The DMA bus is a 64-bit wide bus that connects the CPU directly to the RAM, but it also connects the hard disks and the graphics cards directly to the RAM, so that the CPU can do this. It can create a message. It can say, dear hard disk. Okay, that's called addressing. The CPU addresses the bus, says, dear hard disk, this message is for you. And then the next clock cycle, the CPU says, I want you to get memory from memory. I want you to read the data that the memory is pointing to, and then I want you to put it back in the memory. When you're finished, tell me that you're finished. And then the CPU just goes off and does its own work, while the hard drive reads main memory all by itself, loads the data off of the hard drive, puts it into memory, and then notifies the CPU, okay, that memory is ready. And this amount of time on a rotating medium hard drive, the amount of time to the CPU is like 100,000 years on the rotating hard drive. It went out, it had to spin the disk, and it read the data off the disk, and then it finally wrote that data back to the CPU. The CPU has done 100,000 years of work in the time, if it had that work to do, waiting for the hard drive to get done with that. Okay, so graphics cards benefit from a similar property. What happens with a graphics card is the CPU pre-configures the memory space. The CPU says, over here in memory, at a particular address, it's called, and we'll get deeper into that. Over here in memory is the block that's my 4K display. and which really isn't that much memory. My 4K display is 2,000 pixels across. No, 4,000 pixels across and 2,000 pixels tall. So that's 8 million pixels. Yeah, there's 8 million pixels. And each pixel, and this is very specific, it depends on exact configurations. In the generic case, each pixel has 1 byte for the red channel it needs to display, and 1 byte for the green channel, and 1 byte for the blue channel, and then 1 byte for something called alpha. So it's 32 bytes. Remember, a byte is 8 bits, and a bit is a wire, right? It's a 1 or a 0. A byte is 8 ones or zeros. And then 32 bytes is 4, or rather 32 bits is 4 bytes times 8 million pixels. Gosh, what's 32 times 8 million? Let's just call it 256 million. I bet that's it. Because numbers in computer space always go up by powers of 2. 0, 1, 2, or rather it's 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, 8192, 16384, 35, 530, no, 570, 568, 35, 568. So 64,000 something, that's the edge of how far I can do that. But every number is some multiple of those because it's all just wires. A wire that's a 0 or 1, another wire that's a 0 or 1. So anyway, we figured out that there's 256 megabytes of data required to display my 4K display. And what happens is my video card has its own copy of that memory, and it displays it. It's got its own internal clock cycle that's worked out over the HDMI bus that's plugged into my TV, and the TV has a CPU on the other side of the HDMI bus to load the data. And every clock cycle, if there's a change in the memory that makes up my computer display, my video card sends that over to the TV, and it changes a pixel. Okay, but the CPU also knows exactly where that memory is, and they're sharing it over the DMA bus. I think they might even have their own dedicated bus that's even better than the DMA bus, so that the CPU and the video card can access the video card's memory at an exceptionally high rate of speed, much faster than the CPU's clock is. I'll have to look that up. So what happens is the CPU can read a block of memory from main memory, work on it, modify it, and then write that data to the video card, or send an instruction to the video card to write the memory itself. That's called a shader program. And then the CPU doesn't have to do any work on it. And that's how you get really fast 3D cards, 3D programs. All right. So that's the basic architecture of a system. And I got this picture of, this is a Core 2 Duo system I've got in my office, and it's not nearly as powerful as the modern equipment, but it gives me a chance to point these things out. If you haven't worked in IT before, this fundamental layout is in your computer, I promise, with 100% certainty. There are changes if you have a more expensive computer than this one, and the odds are you do, because Core 2 Duo is pretty weak. This computer is basically worthless. It's worth about 80 bucks, maybe. But the computer that you're running is a direct descendant of this design. If you have a laptop, it's got all the same stuff in it. It's just smaller. Everything about this computer is exactly the same as yours. So underneath this big black shroud is where the CPU is. And CPUs consume a lot of power. Depending on what they're doing, they can consume up to 200 watts, I think, the modern CPUs, which is a third of a toaster. So if you had 3 CPUs and you wired them together just right, you could toast a slice of bread with them running at their full power. Anyway, that generates a fair amount of heat. So under this black shroud, there's a great big fan that blows out the back, and it sucks cool air over the top of the CPU to keep it cool. Heat dissipation is one of the main limitations in building faster and faster computers, because the smaller you make the chip, the more electricity you pack into a tiny, tiny, tiny space, right? The hotter that space gets. And if it gets too hot, the electrons that are traveling up and down on those tiny little semiconductor wires that aren't actually wires, they in a quantum dynamics principle fashion jump from one wire to the next. So the hotter it gets, the slower your computer goes, because it spends all of its time fixing mistakes from wires, from electrons jumping back and forth, until it gets so bad that even the error checking system stops working, and then it just freezes, which you may have seen if you're geeking with this stuff. All right, so I'll continue with this layout. Underneath this heatsink used to be called a chip called the North Bridge, but they don't put North Bridges on computers anymore. The North Bridge has been moved inside of the CPU. The North Bridge is this PCI X bus. The North Bridge used to be, and I think it might have the DMA bus in it too. I'll have to revisit that, because I've told you this before, this field moves so fast, you will never have perfect mastery of anything. If you were a hardware engineer at Intel, you would not know exactly how the latest CPU works. Okay, but underneath this heatsink is another CPU that enables this CPU to send its data out to the hard disk. And this computer has here it is. The hard disk is located here, see? And the hard disk, it connects to power over this black plug, which has a 12-volt wire, a black ground wire, a red 5-volt wire, and a white wire that I think is some kind of control wire. I don't even know what's on that. Some kind of data, probably. Okay, but then the data that is passed between the hard drive and the CPU travels across this blue wire. And this is a DMA connection. It's not that old. It has direct memory access. You can see the blue wire plug into the motherboard right next to the RAM. The RAM is the memory of your computer. I should have given RAM a little bit more time. I'll come back around to it. RAM's very interesting. It also is just transistors, just like your CPU is. And essentially, it's a grid of wires with transistors at every intersection between them. And I believe it's like 32 wires this way and 32 wires this way. And based on a specific number contained in a 64-bit message, it activates this set of wires and this set of wires, which picks out a specific block within their intersection. And I believe that actually at every intersection, there is a 64-bit word stored there. There's 64 bits. And so what happens is, in memory, the CPU sends a message that says, reference the cell stored at this intersection of wires and this intersection of wires right here. And then in the next clock cycle, so what happens is the memory controller then points at that spot, loading the location, the data stored at that location, into its bus. And then on the next clock cycle, the CPU says, get that 64 bits and put it in me, essentially. And so each clock cycle, the CPU can say, RAM, point at this position, and then RAM, read the data from that position. Or it can say, RAM, write the data from that position. All right, so proximity matters. In these CPUs, things are getting smaller because the distance between two components affects how fast they can go in nanoseconds of time. And so the closer they make things, the better they can synchronize their timings, and the faster they can make them run. So here's the RAM. It's right next to the front side bus. And here's the hard disk controller that's on the DMA bus, and it's right next to the RAM. Okay, so the hard drive, here's what would happen. The CPU would send a message, dear hard drive. That would go to the front side bus, and the front side bus would pass that message to the hard drive, and the hard drive would see it and go, oh, you're talking to me. And then the next message, the CPU would say, front side bus, tell the hard drive to get data from some location. And the hard drive would get that data, or it would get that message and store it. And then in the next message, the CPU would say, dear hard drive, once you get that data, put it in the RAM at this location and tell me that you're done. Okay, and now 10,000 years passes, right? The hard drive controller tells the hard drive across this wire to find the data that's stored at the address that the CPU specified, reads the data, and then writes it to RAM directly without needing the CPU's help. And when that's finished, there's a special wire coming from the hard drive controller called an interrupt controller, or an interrupt signal interrupt pipe, I'm not sure. There's a single wire that connects through that hard drive controller, through the front side bus, all the way to the CPU. And when it's done loading data, it just flips that wire and says, "Dear CPU, I got the data." And that's an interrupt. It's a physical event that changes the CPU's operation, that causes it to load instructions from another place and resume reading the data that it told the hard drive to read a while ago. This chip right here is probably an Intel graphics controller. It also might be the south side bus. And the south side bus connects with these ports over here. And this is the only one of these ports that's modern at all. I think these are PCI bus ports, but that's really very old compared to the modern stuff. And this is called an AGP port. That's where the graphic card gets plugged into. And this AGP port shares the DMA bus as well. And there are wires connecting it inside of this stack of circuit boards so that it too can write memory directly to the RAM without needing to talk to the CPU. But these two white circuit boards, they can't do that. They have to write memory to the south side bus and then wait for the south side bus to finish communicating with the CPU. All right, you've got your CD-ROM over here. We don't have many of those anymore, but the CD-ROM works exactly the same as these PCI ports do because it does not have a DMA access, and it works exactly the same as this serial port or parallel port, which we don't have on computers anymore, do we? This looks to be audio plugs that are coming out. They have a special little chip for managing that audio and communicating with the south side bus, which then goes to the CPU. And then there are these USB ports. Okay, so the CD-ROM, the USB ports, the audio, and the PCI ports are all located on this bus called the south side bus. It's very fast, and the CPU can read and write data from them quickly, but they don't have the ability to write main memory themselves. All right. Now, I included this picture of the bottom of the CPU because there's two things that you can see here. You can see that there's a whole lot of pins. This is an LGA 1151 socket. And how many pins are on it? It has 1151 pins. Shocking, right? Only 64 of those are for the DMA bus. Only 64 of those are for the I/O bus, okay? And the rest of them are for things like a message that's called an interrupt, that any hardware device can send an interrupt back to the CPU. The CPU, it's very architecture dependent. You'd have to read the white paper on the exact CPU that you want to use to find out how many interrupt wires it has going into it. Maybe 32 of these wires are for interrupts, which means that 32 different devices on the system can register to have first-hand access to the CPU when they need to send a message. Like, well, I can't pick it up because it's connected to my laptop, but your keyboard. When I press a key on the keyboard, it flips a wire inside of the CPU that says, somebody pressed a key, you better read it and do something with it. And the CPU executes it immediately. It halts all its other operations, reads that key, figures out what to do with it. Okay, what does that leave us with? Like another 1,000 wires to go? Okay, so these 1,000 wires all handle things like voltage management. Okay, you can see that there are dozens of capacitors on the bottom of the CPU. And that's because on that little bitty piece of silicon, the currents that are flowing in those wires, they have to be very, very, very steady. And I don't remember exactly what voltage they need to be. When I was a hardware geek, it was something like 1.85 volts. And all of these capacitors, and probably like 400 of these wires, are dedicated to providing power to the CPU and then smoothing it out so that the power that goes into that 64-bit bus on the CPU is very, very steady and very, very predictable. Okay, now this next diagram is interesting. As for the other 500 pins, I don't know what they're for. They're for power regulation. They're for communicating with the different components that the CPU knows about. But they're all going to happen over a 64-bit word, essentially. Now, this diagram and the next one, I'm a pretty big fan of, all right? This is an image from Intel for, I believe, a Kaby Lake CPU, which is an i7 CPU. It's pretty modern. It's not the latest. They have code words for every CPU generation, and they change the architecture of the CPU every time. The only thing that they keep consistent, usually, is the interface between the operating system, or between the CPU and the operating system, so that we can load up Linux, we can load up OS X, we can load up Windows, and Windows will know which wires need to be twiddled on that 64-bit outside bus that faces the CPU in order to drive it. But inside of the CPU, it's all total mystery. The CPU can do anything it wants, and it does, all right? So these components of the CPU, I want to go over real quick. I'm starting to run out of time, so I will finish this discussion of these two images, and then I'll leave you to read and prepare for the next lecture. All right. This is a 4-core Kaby Lake CPU, and what that means is that each core is able to more or less do everything. Each core has full control over the computer system, except that they have to share this I/O controller, and they have to share this memory controller, and they have to share this GPU, which is kind of like the built-in, Intel 4000 graphics processor. It's way better than not having a GPU, but AMD's, or rather NVIDIA's version of this GPU is 30 times bigger. It's the same thing. It's got 30 times as many of those elements inside of it, and they're connected over DMA. All right, this ring interconnect in the middle is transistor circuitry that enables the CPUs to talk to one another. That's what that circuitry is for. And the CPUs have their own private messaging system. They have their own private language that no one on Earth knows, except for the people who work at Intel who built it. But that's what the ring interconnect area is for. And it's physically located so that the CPUs can do what they need to do in minimum latency, so that they can do it fast. If they moved this CPU over here for whatever reason, its algorithms wouldn't work. Like the hardware design inside of it wouldn't allow it to communicate properly with the other CPU cores because the latency would be so much bigger. And that's what we're dealing with here. The size of this chip, let's go look that up actually. Kaby Lake quad-core die size. All right, so this is called the die, and it's manufactured like 100 at a time from big, beautiful pieces of silicon dioxide using these incredible lithography machines that cut scrapes in. This is the semiconductor we're looking at right here, and it's made 100 CPUs at a time using a laser projector machine that can cut a gap, cut a trace in the surface of the silicon dioxide that is smaller than a wave of light. It's smaller than the wavelength of the smallest wave of light we can generate. It overlaps two of them together so that they cancel each other out, so that you get an even smaller piece. And it cuts the silicon dioxide in tiny, ultra intricate designs in order to enable all this stuff. And that chip that we are looking at, it said right there it was 123. Here we go. Kaby Lake quad core on the 1151 is 35 millimeters by 35 millimeters, but that's the package. Okay, that's almost 4 centimeters. That's not it. Yeah, so the traces that have been cut on the silicon are 14 nanometers or bigger. There are 11 layers of silicon dioxide and other semiconductors that they identified they needed to stack them in this die. Yeah, it's got 24. This particular one has 24 GPUs inside of it. There's 8, 8, and 8. And those are matrix multipliers. We'll get into that more. Let's see. I'm disappointed, though. It's not telling me how big it is. It's 123 square millimeters. So that's 1 centimeter, right? It's 12 millimeters on one side and 10 millimeters on the other. So it's 1 centimeter square. And let's see, count. Transistor count. Is it going to tell us how many transistors? It doesn't say. We could find that somewhere else. I believe it's something like 4 billion. So there's 4 billion slices in the silicon dioxide that in groups of 2 or 3 make a logic gate. And so it's 4 billion divided by 3. There's 1 billion logic gates in this little space. All right, I have to keep going because we're running out of time, remember. The level 3 cache. All right, cache to a CPU is the best memory that exists. Okay, main memory, RAM, is connected by a light year worth of electricity. It's not a light year, obviously, because it really is light. It moves at the speed of light. The RAM is connected to the CPU by a long distance, inches of wiring. And so the time it takes for an electrical signal to go to the RAM and come back causes a substantial delay in how much work the CPU can do, because its clock is going up and down 3 billion times a second. So what the CPU does is that it reads memory from main memory, and then it places it inside of its caches here. I believe the level 3 cache is the slowest cache that belongs to the CPU. So as soon as the CPU reads RAM from that 64-bit DMA bus, it writes it into the cache here somewhere. And then whichever core asked for it, it gets written into the cache near the core that asked for it. And then whichever core that asked for it is able to read it and do arithmetic on it. That's all that the CPU can do. It can do read memory, write memory, add 2 pieces of memory together, subtract those pieces of memory. That's basically it. And then it does that in a very sophisticated way to build all of your computer. It does that a lot to build it all. All right, but inside of the CPU, there's a level 2 cache. Maybe that's this. And it's an even smaller block of memory that the CPU can read and write from even faster than the level 3 cache. And then finally, there's a level 1 cache, which is the main memory of the CPU. It's the memory that the CPU uses for every operation that it has. And I don't, well, we've got it right here, cache. All right, it has a level 0 cache. And I don't know what this is, micro operations. It's got 1,500 micro operations in the level 0 cache. Here we go. The level 1 cache has 32 kilobytes, which means that it's a power of 2. A kilobyte actually means that it's a power of 10. So it's got 32 kilobytes in the level 1 cache. There are 64 sets of 64 bytes inside of it. So what are we looking at here? That there are 64 sets of 64 bytes in an array of memory here. It's got a level 1D cache. I don't know what that is. Here's the level 2 cache. It's 256 kilobytes, so it's substantially bigger. And then finally, the level 3 cache has 2 megabytes per core, right? So this strip with this strip is the level 3 cache for this core, and this strip with this strip is the level 3 cache for this core. All right, now these cores are wired to the system agent, the I/O controller. And it's calling part of this the display controller. Maybe one of these big blocks of memory is the frame buffer that's going out to my screen. Okay, so the CPUs, when they want to send a message out to my USB controller, or probably not to my headphones, to a hard drive that's plugged in over USB, or anything except for the RAM, the hard disk, or the graphics card, it is wired to this big CPU that can address any device that gets added to the system, that can asynchronously, that is, the CPU can be doing work while the system agent is talking to the USB mouse without them interfering with each other at all. It's a whole nother CPU located inside of the system agent. And then when the mouse is finished with its command, or when the user presses on the key on the keyboard, it activates an interrupt in the system agent, which tells whichever CPU is interested in that particular piece of hardware to work. Okay, here's the memory controller. This whole machine is responsible for addressing the memory that's located on that DMA bus, and then reading and writing memory from it, and then notifying which CPU asked for it when it's ready. And then the GPU and the media capabilities has to do with doing specific kinds of mathematics, so that you can either display 3D images really fast, or you can decode video data really fast. Because if you're watching like an M264 video off of YouTube, the size of the video is much smaller than the data size that you're actually going to get displayed. All right, so finally, to finish this, this mini sprint, here's the same diagram. All right, this is the same CPU, but it's been diagrammed in a way that shows behaviors a little bit better, and it's also been flipped. All right, so notice that it's been flipped. This Gen 9.5 GPU is on the left to me in the diagram, and it's on the right to me in the CPU image, in the die image. All right, so you can see, let's see, I suppose that without having more documentation, the most interesting thing to point out is that the display controller has the most bandwidth, and it's located inside of the system agent. The PCIe controller has the second most bandwidth, located over here inside of the system agent. It's another CPU. It's another computer that handles jobs. It delegates jobs for the 4 CPUs inside of the system. The extended DRAM controller, I'm not sure what an extended DRAM controller would do. And then finally, the memory controller. Now, the memory controller has a smaller number of connections because the memory is directly wired to the CPU. The memory controller is for telling the memory what work to do. It's like a control bus, but it's not the data bus. The data bus from the memory is fat and full, and it's always full of data. And then it uses another pipeline on the side in order to communicate. So that's your first pass into computer architecture. Continuing on in this document, this CPU Kaby Lake architecture on this page is really cool. It will certainly make your mind pop if you progress through it. Elements of the CPU are very valuable for you to read up on, and we will talk about them in the next lecture, leading you up to building in JavaScript a very simple CPU that can execute some instructions. Now, these instructions are wires. That's the thing that you have to keep in mind. They're just wire settings, and each time the clock ticks, the CPU does something with those wires based on physically connected semiconductors. Anyway, this is Lambda School, Computer Architecture 1. We'll see you later.